Okay, great, thank you. So I'd love to talk about DESI, but it's been on Sky for weeks, so that's just old news now. So instead, I'm going to tell you about a conceptual design for something that could give us 10 times the capability of DESI. Okay, so probably you've seen a curve like this before. So this is just plotting the size of redshift surveys as a function of time. And the first time I made a plot like this was probably in Mark Davis's office upstairs around this year. And unbelievably, we actually have been on this curve of 10 times larger catalogs every 10 years. So if you're doing some calculations that you think are going to be super, super important in 10 years, don't do it based on the size of whatever sample today, but like really, I think we're going to stay on this curve. We're most of the way there. Okay, so here I just want to make the point that these optical redshift surveys, they're actually pretty easy. Americans in the audience, they won't laugh at this because they know, like as kids, this is what you do on vacation growing up in the United States. It's, yeah, just shooting fish in a barrel. If anyone isn't from here, this is what we spend our time doing. So the point is, it's just pretty straightforward. So for these optical redshift surveys, it's just the point when you look at maps of the sky and what these galaxies look like, it's really not technically challenging to map out in 2D and 3D where these galaxies are. So we're not talking about CMB maps where you're at a part in 10 to the 6, 10 to the 7. These are objects where they're comparable to the brightness of sky, and it's actually the current catalogs, we're only just getting at the point where we're mapping out the galaxies that are fainter than the sky. So we're still in this regime where it's pretty easy. If you pick any individual object here, you could ask any number of people in the building, could you get me the redshift for, like, I really like this galaxy over here. Could you get me the redshift? They can get you that redshift. The only hard part is when you want millions of them and you want to do it cost effectively. So it's really a matter of doing it cost effectively. Okay, so, oh yeah, so want to just make a comment about systematics also. So systematics as well, because we're in this regime where it's pretty easy what we're doing, there is a way to mitigate systematics. So there are the spatial systematics that come from these imaging catalogs. We can mitigate them observationally. It would be easy to make them worse than what we have today, but it's also possible to make them better. And so, for example, photometric calibration, we're talking about like, yeah, 1% kind of calibrations. That's pretty easy today. You can do worse than that, but then you screwed up. You can do better than that. So I think the best large field photometric calibration right now is from the WISE infrared galaxy catalog. So they have photometric calibrations that are about a part in 1,000. But technically, you look at things like planet microlensing surveys where there you're measuring how bright things are to a part in 10 to the 6. So technically you can do these things. It's just a matter of what's the driver, what point do you have to get to. Spectroscopically, same thing. Pretty easy to get redshifts of galaxies. This is a real DESI spectra taken recently right now. I'm not showing the spectrum of a galaxy because this fiber must have missed any galaxies. There's no galaxy light here. But the point here is that the systematics in redshift space, they come from the sky brightness. And the sky brightness from the ground is primarily in these delta functions of sky brightness. So for all intents and purposes, these are delta functions in wavelength. And if we disperse the light, then we can work between these skylines and mitigate this problem essentially as well as we need to. Okay, so let me get on to this mega mapper concept. So this is an idea that we put together, submitted to the decadal survey just last year, primarily written between DESI collaborators and Carnegie observatories. You can ask what the experimental landscape will be for these redshift surveys in 2030. So hopefully DESI, Euclid, W first, they're completed. We have CMBS4 underway, LSST hopefully is well underway at that point. And at that time, 10 years from now, the bulk of the deep sky imaging from which you'd select any targets for a project like this will be in the southern hemisphere. So it's just a map, sorry, this is a sky map, northern sky, southern sky. This LSST footprint, it's still not entirely defined yet, but it will primarily be in the southern hemisphere. Okay, so today, literally today, the fastest redshift mapping machine, it is this DESI spectrographic KIT-Peak. If you haven't seen it, it's pretty cool because it has this transparent dome. Not really. It would be though. So you've already heard about this. This mega mapper concept, the concept here is this is something we put in the southern hemisphere so that we could take advantage of the LSST imaging available at that time. So briefly, the idea is to get to this 10 times speed with a combination of a bigger collecting area on the telescope and a higher multiplexing factor by a factor of 4. So this is a picture of right now, these are the Magellan 1 and 2 telescopes. I actually don't know which is which. But so this is in Chile, and our design is based off of exactly the design of these particular telescopes. So this is a 6.5 meter diameter primary mirror. And so this would give us this collecting area that's 3x what DESI is. And then we'd make a focal plane system, which would be down here. That would then, instead of 5,000 robots, would have 20,000 fiber robots. Okay, so this design really hit high gear once we've found optical designs that worked with this primary mirror. So this is exactly a primary mirror, the same primary mirror that's on the Magellan telescopes. That's a very cost-effective, I think it's the most cost-effective primary mirror per unit collecting area that's been made. That's not spherical, I should say. So it's based upon this design and then an optical system that can correct a field of view that's 7 square degrees on the sky. Okay, and furthermore, this design has been done in such a way that the focal plane on the back of the telescope, so where you mount this instrument, optically looks identical to what we have on DESI. So what we have here is, this is a telescope design that's been built several times already. A correcting system that's new, but then a focal plane feeding instruments that could be literally identical to what's already been built for DESI.
Sorry, there's going to be a 1.2 mirror lens.
Yeah, no, so these are big lenses. So this is
This will be the biggest lens in the world.
LSST has well, so right now DESI actually has the biggest lens on a telescope. LSST has a larger one. This is comparable to the LSST. That's right. It's not trivial. I didn't claim it was trivial.
What's the fiber on the sky?
What's that?
What's the fiber size on the sky?
About 1 arcsecond. Yeah. Okay, so this is just a rendering of what this would look like mechanically. A stack of spectrographs where, because we're doing this design to match optically with what DESI has built, that means you would have the option of reusing the 10 spectrographs that we've already built for DESI. And what I should say is those designs were finalized about 5 years ago. But if we had to rebuild spectrographs the same spec today as what was the design 5 years ago, we actually wouldn't change anything. So they're very, very good designs. You might have expected we've gone on Sky. There are things that you'd want to improve. Actually, they're pretty darn near perfect. So even if you're building things today, you would build the same spectrographs. And in fact, the SDSS-5 project is doing exactly that. So the spectrographs that have been built in France, SDSS-5 has started an order of 6 more of them. So they've just kept this assembly line going of building identical units. Okay, and here's a picture of some of these spectrographs. So this was installing, I don't know, number 9 or 10. So this is a room where these are all these spectrographs, cooling systems built by Saclay, by Christophe, who's here somewhere. Anyway, so all these are performing wonderfully. Okay, the site would be Chile. And in fact, the site that we're looking at is a site that was in the Giant Magellan Telescope down select. So on Google Maps or Google Earth, this is what the site looks like. So it actually used to have a sub-millimeter telescope that has been removed, but there's a site here with services that could be used. And then this is a comparison of étendue to various existing and proposed projects, and one can push on this, but I just, and maybe some of these numbers have changed, but I'd certainly invite everyone to push these numbers up as far as possible going into the future. Okay, so these should be the lower limits of what we're talking about. Okay, so the R&D that would be necessary to make this happen is this focal plane system. So this is the multiplexing, this robotic system that moves fibers around and repositions the objects in the sky. So this is a picture. I mean, you can't see anything here, but kind of each pixel that your eye can pick out, that is a little robot moving around a fiber. And so this is deployed on the telescope. This is a hard picture to take. This was just taken a couple months ago after everything was installed. And then there's no more access. It's like all closed up in the telescope, but there's like a little peephole that you can open up and stick through your iPhone and kind of like get a camera looking up through this little peephole. That's how this picture was taken. Before it was installed, this is what a segment of this looked like. So this is 1 of 10 pie slices out of that focal plane. So this has 500 of these little robots, and they're put on a pitch of every 10.4 millimeters. But this system is being commissioned right now, but functions very well. For MegaMapper, what we're looking at is something that would have to be smaller and more affordable. And the scale that we're looking at to fit on this design is a 6.2 millimeter center to center for these robots. And it turns out this is actually exactly the packing size of number 2 pencils. So if you want to know what MegaMapper looks like, it looks like number 2 pencils, but probably expensive pencils, but hopefully not too expensive. So this is R&D that's underway right now by actually the same members who did this R&D for the DESI project. And they're working with 2 motor vendors right now to kind of prototype the motors, the components that would be needed for this. So this is, I show this because this is the one funded part of the project right now, is to do this R&D. So whether or not MegaMapper happens, these robots will be designed and built, and hopefully will offer an affordable option for either this project or another project in the future. Okay, so this is our notional timescale. So again, this is just the conceptual design right now. So this was submitted to Decadal Survey for consideration of what science reach is possible. We think we've outlined a program where it could be completed on a time scale 10 years after DESI project. So it's actually, when we worked this out, we said, let's say that all of the dates are take DESI project, add 10 years. And for the telescope, we took the Magellan 2 telescope and we added 25 years. And then we just said, use all of the dates along the way. And this is what it works out to. That's it. That's all I have.
Any questions for David?
There won't be any questions.
KG?
I have a question and a comment. So the question is, it's not clear to me how you get 4 times more multiplexing out of 1.6 times. Because you said that there's going to be multiplex of 20,000, but then in terms of spectrographs, you say you're talking about 10 DESI spectrographs plus 6.
And then we would build 16 more. Yeah. And then the details here, and then we put in a few more fibers per spectrograph. Now that we know exactly what the data looks like, we can push a little harder on how they're used.
My comment is that you're underestimating the gain in spectroscopic efficiency because the site and the fiber size matters.
Mm-hmm.
So working at compounders here are a factor of 2 faster than KP.
So there is a speed just because the
so I
the
think
seeing is
like
better.
20 times faster than
All right, I'll take it. Another factor or 2. Come on, hit me. All right.
Any other questions for David? Elena?
Oh, I thought Mike Wilson talked about that already. I missed what he said. The science from this. Yeah. I cut that out entirely because I thought you covered this.
Slide from yesterday, I think it was Martin put a lot of the numbers, and also Simon and a few others we did as an astro.
So one thing I'll add to that is there is a fair amount of flexibility in instruments like this, just because since these are targeted surveys, right? We can target whichever objects we want. So even even when you're close to starting, you can adjust your program to pick the redshift range or target classes or whatever that you think are best. So I do view that as an inherent advantage of instruments like this. Okay.
All right, let's thank David again. Next, we have Kyle talking about SpecTel.
Okay, so I'm going to present a white paper that we submitted to the decadal survey, but more than focusing on the particular project, I'm actually going to step through the different cosmological science drivers we could be considering and really just pose a lot of questions that I think we can go over in the afternoon panel. So don't ask me why I'm using the DESI background, but this is not the SpecTel telescope. Okay, so what I'm going to present is just kind of an overview of what I think we need to do as a community as we look forward for planning the next large program. I'm going to really keep fully within the boundary conditions of a DOE world. So it's going to be ground-based facilities, and it's going to be tied to things like the snowmass process. So I'm going to talk about the timeline and a little bit of what the current status is, some other work that's been going on concurrently. Then, as I mentioned, I'm going to really just pose a lot of questions to the audience. We won't answer in real time. We can answer in the afternoon maybe, but what should we be asking ourselves about what defines a stage 5 spectroscopic survey? Okay, there's going to be two regimes. You want to think about what's at the high redshift regime. That's, for example, MegaMapper, sampling, exploring non-Gaussianity. There's also the low redshift regime, where you're in the accelerated expansion of the universe. What science is to be gained there? Okay, I'm going to talk a little bit about the SPECTEL design and how I believe it could meet the most ambitious cases for stage 5, covering that full redshift space, redshift 0 to 4. And then, as I said, this will just seed, hopefully, some of the afternoon panel discussion. I know the others on our panel have some other questions complementary to what I'm going to present today. They're also very good for that panel discussion. Okay. So here is kind of an alternate view on a timeline for experiments compared to what David just showed. This is sticking with a snowmass process for finding the motivation for the next project. We're not at CD0 right now. I don't expect to be until after snowmass is over. So you can imagine the way the alignment could be is a little bit less optimistic than what David presented, but for stage 5 spectroscopic survey, construction can't really begin until something like 2025, 2026, if you go through that process, which means operations from the mid-2030s to mid-2040s. And why do I care about all this? So I become eligible for Social Security about here, like right in the middle of the blue. So the way I look at this is whatever comes out of snowmass and whatever comes out of our next planning is my last project of my career. So I'm interested in see where our field goes. Okay. This also, I mean, more globally, this is probably the only source of DOE dark energy and inflation science until after 2040. Once you move past the stage 4 experiments, I'll show some other possibilities as well in a second. But okay, so that's kind of background of why I care. Now, in the last few years, there's been work on future planning in several different incarnations. There's been the Cosmic Visions Dark Energy panel. We've thrown out a few white papers. I think mostly the outcome is just kind of awareness building about looking forward. We just completed this workshop where we had to justify reasons for instrumentation development for the next 20 years. That was a month ago, so that was this basic research needs for instrumentation. I believe we'll post the white paper in a month or two. I just got some feedback a couple days ago about edits to make. So what went into that what comes out of these processes here, the cosmic visions, the basic research needs, are one, it's just a really broad goal. What do we want to do after DESI, LSST, and CMB stage 4? We want to probably explore the largest volumes that are possible. We want to optimize cosmological information. We want to get a large range of spatial scales, and we want to get a large range of redshift. Those are really generic statements. So what I'm going to do is I'm going to drill down into those and what they mean scientifically in the following slides. Which one? Not yet. This is from the white paper that is for this basic research needs workshop. This was across all of high energy physics. So it's going to be a long, tedious document. Let me just tell you. I think it's going to be available maybe in March or so. So from our community, from somewhat of a random walk, there was 3 basic ideas that went through of how to meet these goals of doing a large survey, large spectroscopic survey. So optical and infrared spectroscopy, which I think a lot of us here are genuinely interested in. Notice that I commented out the size of the sample for now, but basically to get spectra at decent resolution to high redshift. And then there's some technical requirements to get there we don't need to focus on. So the other 2 ideas that were suggested were 21 centimeter intensity mapping, which I think most people in here are familiar with. And when they paint their data samples, what they're saying is that their constraints on the power spectrum are going to be comparable to a 2.9 billion galaxy survey out to a redshift 6. So that's kind of the ambition of the project that the 21 centimeter community is painting. Now, there's another possibility out there, which is millimeter wave intensity mapping. So it's using CMB-like detectors. And this is fairly new. A lot of it's coming out of the galaxy science community. And what they paint is this picture where they can obtain enough signal that's comparable to flux from like about 1 billion galaxies over the same redshift range. So there's a lot of complementarity here, right? These are both intensity mapping, same redshift range, comparable data sizes. Optical IR spectroscopy, I think we need to ask ourselves what we want to be. What is this project in the next 20 years? Okay. So now, taking these broad statements about mapping the universe and mapping them onto science drivers. So this is our figure for congressional aids. The y-axis is the clustering scale, and I prefer K, but here, because people don't understand in wave number, we use megaparsec. So of course, small scales up to large scales as you increase in the y direction. And the other observable parameter, of course, is redshift. And what we did is we mapped different observables onto this parameter space. Okay, so I'm going to show this plot like 7 times. It's going to basically be the transition slide as we discuss each science driver. So let's just go over really quickly what's on here. Here is what most of our spectroscopic surveys are designed towards right now. So this is baryon acoustic oscillations, of course, and DESI, to first order, is saturating information using that technique out to redshift 1.5. Okay. So using a little bit of artistic license, I'm going to claim that everything that DESI is exploring is the accelerating epoch. So redshift 0 to 1.5. That's where you can see a transition from matter dominated to dark energy dominated. And as I said, I'm using artistic license. You can define any boundary condition you want here. But no matter what, you're in the dark energy dominated regime in this end. So when we look at the rest of the parameter space, you keep on large scales, move to higher redshift, you get to inflation. Or you can keep probing the BAO scale out to infinity, okay, if you had the technique to do so. Neutrinos, of course, we're going to be exploring with growth of structure. You can get them down here, but I'm going to highlight them in this regime, as I'll come back to shortly. And then at smaller scales in the local universe, there's growth of structure as a test of modified gravity, also anything with accelerated expansion. So dark energy, so on and so forth. We also should ask ourselves, I'm not going to cover it in this talk, whether or not we want to build something that's complementary to the dark matter community. So following up on David's presentation, MegaMapper is, and SphereX, and a lot of these other projects, including 21 centimeter, are really focused on the inflationary studies. That's large scales and fairly high redshift. Of course, the idea there is to just use the large volume that's available. There's also possibility to test different models, some niche models of dark energy in this regime, not with these large scales, but down in smaller scales, BAO, for example. But notice that if you build a program in this regime, dedicated entirely to this regime, you really are excluding the possibility of exploring the accelerating epochs. Now, each of these science drivers is going to have a really big upside and a downside. So what I think we need as we look forward, we need to ask ourselves both questions. Like, what's the advantage of doing so, but what do we need to be robust against? What do we need to be aware of in terms of possible drawbacks? So on non-Gaussianity, look, I think we all agree that current surveys do not tap into this observable with any real precision. There's a clear potential to get very vast improvement over current studies. It's also, we have very clear projections that show there's compelling results out there. Michael, I guess I wasn't here yesterday, so I apologize, but you gave there's projections for FNL from a spectroscopic survey yesterday. Okay. So on the downsides, it is, of course, a very weak signal, and it might not even be there. The spectroscopic, if you look at it from the spectroscopic side, these targets are extraordinarily faint. They're high redshift. We're going after a single line or possibly continuums, I'll say shortly. So they're really susceptible to incompleteness and contamination, at least from a spectroscopic side. So imagine everything that Julian said earlier today and just cut and paste his entire presentation onto that bullet point. Can we control all those questions about our data quality at the level where we're measuring down to K modes of like 0.001 with the precision that's needed to make an FNL measurement? Okay, so that's something we have to be really aware of. And if we're right on the hairy edge of the imaging data or the spectroscopic data, and we go out and declare a non-zero detection of non-Gaussianity, are we going to believe ourselves? And anybody else going to believe us? So we have to be really aware of this. So questions for everybody in this room is, what do we require in these measurements to guarantee that we're making a robust measurement? So I just made up a few guesses myself. Do we need to have consistency in samples split by redshift, by data quality, by target class? Do we need to have consistency between 3-point statistics and 2-point statistics? Do we want to have some multi-tracer techniques with varying bias to alleviate cosmic variance? I don't know the answers, but I think if we really want to make a FNL program, I think we need to know what is required to make sure that it is a robust measurement at the end of the day. So my next parameter space, or my next element in discovery space, is BAO at higher redshift. As I said, DESI saturates this at redshifts below 1.5, at least a first order, but there's a lot of room for improvement at higher redshift. So again, just as in the last bullet point, anything at higher redshift has obvious potential for improved statistics. The other nice thing about this feature at high redshift is the signal is intrinsically robust against the same systematic errors that I just talked about on the FNL measurements. It has a peculiar feature. It's hard to reproduce that with fluctuations in imaging or spectroscopic data quality. So I think we don't have the same concerns about making a measurement. But on the downside is back to the point of what redshift range we're exploring here. This is purely the matter-dominated era. It gives you very weak sensitivity to dynamics and cosmic expansion due to some models of dark energy or modified gravity. That, we have to ask ourselves, is that a compelling motivation in itself to pursue the sample? I think at the end of the day, Mike says we get improvements on dark energy, but that's really through degeneracy breaking. I believe it's probably through omega matter and omega curvature and curvature degeneracies. You get general improvements on your other parameters. Is that in itself a sufficient motivation? Okay, the next bullet point at higher redshift is how far down in number density or in spatial scale do we go to do measurements of the growth of structure? I think the primary driver here is neutrinos. Again, lots of data there. We should chase it. It offers a separate path to measuring neutrino masses that's independent of CMB optical depth. I know the projections are out there for what could be done by looking at the evolution in the power spectrum due to neutrino free streaming. I don't know how they compare to things with and without the optical depth from CMB, but other people know the answer to this. But it's a good question to ask. But on the downside, again, neutrinos alone, are they sufficient motivation, right? We asymptote towards a minimum mass scenario. And as we keep building more and more experiments, you just reach that asymptote. And what's the point of diminishing returns? How far towards that scenario do we want to go? It also likely requires very, very high number densities. If you're really going to try to do something independent of CMB optical depth, you're going to need a lot of objects. And I don't know the answer to this either, but is there science associated with modified gravity with measuring clustering at high redshift? I don't know the answer to that. I suspect it probably only gives you an anchor for interpreting the low redshift regime. Okay. So those are the science drivers at high redshift. Now there's knobs to turn on what type of samples we would require to get there. So from optical spectroscopy side, there's two target classes. There's Lyman break galaxies and Lyman alpha emitting galaxies. And the number densities roughly are 1,000 per square degree if you go to a limit of 23.5. And you get about a factor of 10 more if you go a magnitude fainter. Okay, so I very specifically am choosing these limits because the paper that Michael and Martin wrote makes projections for the spectroscopic completeness for a 6.5 meter telescope. And what you see is that in, sorry, the blue is not showing up very well here, but the blue is right here basically. That's a 1500 second exposure. And you basically get a fairly complete sample at an R band magnitude of 23.5. That's Lyman bright galaxies, not Lyman alpha emitting galaxies. That's the bright galaxies. If you want to go a magnitude fainter to 24.5, you get 10 times as many objects, but you need to go now to a telescope that is bigger by a factor of 3 and has longer exposures by a factor of 3. So you know, to get that magnitude, you need a lot more collecting power and time. You need more photons. Okay, so which number densities do we want at high redshift, 1,000 or 10,000? Again, this sample is going to be dominated by Lyman bright galaxies, and our redshifts are determined by absorption, which is why this makes it a very challenging probe. I also personally think these projections are probably optimistic because the lines are actually far more complicated than was built into the templates. Okay, so what sample do we need to guarantee we have a robust stage 5 program? Now, if I want to convert these numbers into facility requirements, basically, if I count the exposure time plus the number density, if I want to go to 23.5, something like MegaMapper will be sufficient. If I want to go to 24.5, you're now at the regime of needing 140 million fiber hours. And that gives you something that requires 10 times the collecting area of DESI and 10 times the multiplex power over DESI. Okay? So 100 times DESI to get into that regime. So now that's the high redshift side. I found, when I read through all the decadal survey white papers, that there was actually a pretty deep neglect of the science that could be gleaned, at least from a cosmological perspective, in the accelerating epochs. Okay, so that's down here. That's redshift 0 to 1.5. And the techniques would be, of course, galaxy clustering at high number density. Now, again, upsides and downsides. On the upsides, there's lots of targets available from imaging data. That's easy. The other upside is this is the regime where you can span the transition from matter dominated to dark energy dominated and make a new generation of experiment exploring dark energy. It can complement LSST. This is where LSST sweet spot is from the weak lensing science. And it's possible there's new physics in this regime. Now, downsides. The low-hanging fruit in terms of cosmology studies are already taken, both from LSST, Euclid, DESI, weak lensing, BAO. To really make a major advancement, you need very sophisticated modeling. And it's impossible, I think, at this point to really project forward what we're going to learn about dark energy in this regime. So those are, I'd say, the downsides. But I think we can ask ourselves where we want to go. So I'd see 3 choices at low redshift.
Sorry, the sign is split.
Okay, so I'm cutting and pasting, as you can see, and the sign should be less than 1.5. So we have 3 choices. We can do nothing. We can say we've saturated at stage 4 and there's no dark energy science at stage 5. And just focus on the high redshift universe. We can do a targeted, more subsampled program. It can be, I don't know, it could be a pencil beam survey to calibrate LSST. It can be Sharpie. Yeah, Sharpie beam. Yeah, exactly. It can be a Sharpie beam. It can be target observations of clusters, voids, filaments, whatever. It can be photo Z calibration. All of these, they're really just supplemental ideas. I think there's a lot of value in them, but they don't require a dedicated facility. There's ways we could use existing facilities or a smaller scale facility to do this. If we want something that's a fully independent dark energy program, you're going to require a pretty large dedicated facility. So that would allow lots of other techniques beyond just 2-point statistics, which I think would really be required to extract more information from clustering. So forward modeling, the density field, I think that came up earlier. You can imagine doing a weak lensing survey from the LSST data, but using the spectroscopic redshifts for every lens galaxy, or every source galaxy. Not lens galaxies, but source galaxies. You can imagine getting complete samples of galaxy clusters. You can imagine how far down in the nonlinear regime can you go. These are the areas where you could explore, and we don't need to know the answers of these today. We're talking about by the year 2040 is when the sample's complete. So what do you expect in the next 10 or 20 years in advancing these techniques, and what sample will be exciting to pursue with the new theory developments? Okay, so how do you actually get there from a observational program? There's lots of target classes available. They span different tracers, different galaxy types, blah, blah, blah. You can do color selected samples, but you can easily get into 20,000 object per square degree regime. Now, to make some other hand wavy estimates, calibrating our DESI rates of redshift efficiency, you move to a 10 to 12 meter class telescope, you increase the number density by a factor of 10, and you're in a regime where you can get 280 million redshifts over 14,000 square degrees, but you require 10 times the multiplex power of DESI on this 12 meter telescope, and you require a DESI-like timescale, 5 years. So the summary is there is a very compelling science case to be made over the entire redshift clustering scale regime. Every science case has a list of upsides and a list of downsides. And we have to ask ourselves, do we just want to choose one regime and focus on it until the year 2040? Or do we want to go super ambitious and build a and require that any stage 5 cosmology program can realize every single upside in this parameter space while also guarding against the downsides? So a facility concept does exist that's possible of achieving that more ambitious goal. This is a white paper we submitted to the decadal survey. It's also, more importantly, a funded ESO study that came out several years ago. The idea is an 11 meter telescope, and everything in the design is optimized for multiplexing power. So you basically put a boundary condition on the facility where you have to have a plate scale and a telescope diameter that's optimized for fibers. You have a focal plane that's optimized for placing fibers. And in the end of the day, if you can get a fiber design, like David mentioned R&D for fiber positioners, but if you get a fiber positioner design that cuts the spacing in half from DESI, you get to that regime where you're on your 12 meter telescope with an order of magnitude more fibers than DESI. So that is the regime that we required for both the low redshift end and the high redshift end of this new discovery space. Okay, and it's called SPECTEL. Here's just a very simple image. And what this would allow is something like 10%, especially over redshift, so something like 10% of the LSST gold sample. Putting it into perspective, here's DESI with this prime. This is the same panel that David showed. You can see it depends on what positioners you use, but if you go to this 5 millimeter positioners, you get 2 orders of magnitude improvement over DESI. Okay, so I really just want to give people some food for thought for the afternoon discussion. The SNOMES process happens in the United States. It's kind of analogous to the decadal survey. It's happening in the summer of next year. I really think if we impose ourselves to be, ground-based spectroscopists interested in cosmology, that's the framework to work in to assess what are Science 5 science cases. And whatever comes out of it is really going to set the stage until 2040. I think important things that we have to really be honest about is that inflation studies really are at odds with dark energy studies. And we have to think about how to balance those two, or whether or not we want to chase both simultaneously with something very, very ambitious. So let's just revisit this type of discussion during the afternoon panel session. But as I mentioned, there's other really good ideas that the other panelists will bring to the table, and I'll take any questions.
Questions for Kyle?
I don't think I agree that necessarily, if you only look at high redshift, you don't do any of that. It depends, if you know for sure that energy cosmological constant, then I agree. And you want to know that value more and more precisely, then I agree with you. This vector omega factor, they can measure that energy. 3 and 4 and 5. In particular, you get 1% measurement of raw dark energy at redshift 3.5, for example. And if anything, if the dark energy is evolving with time, if any weird model, then you want the lever arm, and you do want to study this transition into multiplication and have measurements of raw dark energy at redshift 3, 4, and 5. If to expand your discovery space. So I'm not sure it's. I agree. It would be nice to really have a good measurement across the transition.
So I will acknowledge that I put that in there to be a little provocative. I understand what you're saying, but you're also not just measuring rho dark energy. You're trying to measure d rho dark energy dz. And when you're only making, when it's that faint a signal, it becomes hard at the high redshift end. So right now what we're seeing in the projections from BAO, supernova, CMB is the first order. The BAO gives you really nice constraints of curvature. The supernova give you really good constraints on WA, W naught. And then you combine the two and you get a really, a much tighter constraint in W naught, W than would be expected by either of them in unison, in isolation. So you really see a lot of the advantage of covering the whole redshift range, A, but you also see the power of supernova between redshift 0 and 0.5 when you do these tests. So I think that really highlights the advantages of being in the low redshift regime.
Any other questions? If not, let's thank Kyle again. Next, we have Christoph, who will tell us about MSE.
Okay. Okay. So I'm going to present MSE and the cosmology that we can do at MSE. So MSE is for Mauna Kea Spectroscopic Explorer. A few words about MSE. So what's the plan? The plan is to replace the 3.6 meter telescope, CFHT telescope, and to replace the telescope with a 11.2 meter telescope, and the field of view will be at the order of 1.5 square degree. And this telescope will be fully dedicated to spectroscopy. The number of positioners will be at the order of 4,000 fibers. And for the cosmology, we will use only a part of the fibers. This means something at the order of 3,000 fibers. And we will use a spectrograph with a low and moderate resolution, meaning a resolution between 2,500 and 6,000. And concerning the wavelength range, we want to cover both the visible and the near-infrared range. This means with G, J, and H band. And what we are proposing for the cosmology with Will Percival is a large volume survey of high redshift galaxies and quasars. And we have proposed and presented a white paper. What I'm going to present is really related to what is written in this white paper. In MSc, you have different domain of science. And I think that here the strategy is different than the strategy that we had in both EBOS and DAISY. The idea is that we will have to share the time with other science. And this means, for instance, with exoplanet, galaxy formation and evolution, time domain astronomy. And at the end, the programs that we propose represents only half or 1/3 of the dark time. So what's the context at the time of MSc. You have seen this plot many times. This plot represents the expansion as a function of the redshift and the sensitivities that we can have on the measurement of this expansion rate. And you can see that in the first part of this plot, I mean below 1.6, we are in the cosmic variance regime. So this means that we are limited by the cosmic variance, and above 1.6, we are limited by the short noise. And this is very simple to explain. Here we are using as a tracer the LRGs and the ELGs, and above 1.6, we are using the quasars, and above 2.1, we are using the Landman alpha forest. So this means that there is really a region where we can improve what we have measured with DAISY. So this means that really the target and the goal for MSc is to have a study above 1.6 in redshift. We are the main subject in terms of science for MSc is first the study of the non-Gaussianities. This means the study of the inflation through this parameter FNL. And as you know, we are talking about that during the 2 days. FNL can be expected at the order of 10 to minus 3 for the usual and really the simplest models for the inflation. But if you consider other models with multiple fields, which are not so exotic models, you can expect the value FNL at the order of 1. And really, so this means that the goal for the measurement of FNL is this number. I mean, we want to measure FNL at the level of 1, and this is really possible with this new generation of 3D survey. And so far, the only measurement, the only decent measurement of FNL that we have is with the CMB, and it's at the order of 5. And even you can consider that this measurement was done with bispectrum. Concerning another important subject for us, which is the measurement of the mass, you know, the mass of the neutrinos. You know that with particle physics, we have demonstrated that first, the neutrinos has a mass with the atmospheric and the solar oscillation, but particle physics is not able to give the absolute mass of the neutrinos. And we can obtain this with cosmology. And we know basically that we have two possibilities, two different hierarchies, the normal hierarchy and the inverted hierarchy. What we measure with particle physics is the difference between the different mass eigenstate. And so this means that we have these two possibilities. And if we are in the normal hierarchy, the minimum values that we can expect is at the order of 60 millielectron volt. And for the inverted hierarchy, you can have something at the order of 100 millielectron volt. So this means that if with this project, we are able to achieve an accuracy at the level of 8 millielectron volt, we will be able to measure the mass of the neutrino at 7 or even 8 sigma, and we will be able to measure the difference between the normal and the inverted hierarchy at the level of 5 sigma, if we are a minimal mass at the order of 0. So this is really the plan for this kind of project, the measurement of the neutrino mass, the measurement of FNL, so this means the test of the inflation, and also the study of the dark energy. So what we are proposing exactly, we are proposing a wide survey, meaning 10,000 square degree with 3 tracers covering the redshift range between 1.6 and 4. And the exposure time is typically at the order of 30 minutes. This means that at the end, when you do the computation, what we need is 100 nights per year for a 5-year program. And you can compare this MSc program with the existing program in terms of redshift range, area, and the bar thickness give you the comparison in terms of number of galaxies. So the first tracers between 1.6 and 2.4 is emission line galaxy. So we are going to use ELGs for DAISY. We have used this for EBOS. And for the star-forming galaxies, we can determine the redshift with the position of the O2 doublet. Here, in the case of MSC, we will have near-infrared arm. So this means that we will be able to measure the O2 line for redshift between 1.6 and 2.4. So this means that here we are going to cover a region not covered by DAISY or even by Euclid, because we can consider that the upper limit in terms of redshift for Euclid is at the order of 1.82. And compared to another program, PFS, we are going to multiply by a factor 6 the surface. The second tracer is the Lyman-Wade galaxy. So this means that here we are going to cover a range between 2.4 and 4, and we can talk and we can discuss about this limit 4. We can go further, I think. And so you have different kind of Lyman-Wade galaxy, and a subsample of the Lyman-Wade galaxy are Lyman alpha emitters. In this case, you can see in the spectra that you have a very pronounced Lyman alpha line. So in this case, it's quite easy to determine the redshift. And you can see here, for instance, the estimate of the efficiencies that we get for the Lyman alpha emitters, which is at the order of 90% to get the redshift with an exposure time at the order of half an hour. And of course, when you go to the second category or the third category without emission line, you reduce the efficiency that you can expect. Here it's at the order of between 50% and 40%, depending on the magnitude of the objects. Anyway, with our very conservative approach, we estimate with that half an hour of exposure time, we can obtain 50% redshift efficiency. And if we compare this with Mike's work, in the case of his work, we can extrapolate that what we need is only 20 minutes. So this means that here in this projection and in all the forecasts, we have been very, very conservative. The third tracer is the quasars. Actually, we will use the Lyman alpha forest of the quasars. And if we consider that our magnitude limit is 24 in R, we will expect at the order of 170 true quasars per square degree, which is 3 times more than what we will have in DAISY. What's interesting in this method is that we can use the autocorrelation of the Lyman alpha forest, but we can also use all the cross correlation between the absorption in the Lyman alpha forest and the cross correlation with quasars, as here, or with ELGs or Lyman-Wade galaxies. This is a summary of the targets and the target densities that we will have. So this means at the end, the number of total galaxies or quasars that we have is quite low. It's at the order of 15 millions. It's low compared even to DAISY. But with this strategy, we can measure many points in cosmology. We can measure FNL. We can measure. We can test different model of dark energy, and we can also constrain the neutrino mass. So, what are the forecasts? This is the situation after DAISY, and what we can expect with MSC is that this means that we are going to cover this region from 1.6 to 4, and here you have 12 measurements with a precision better than 1%. Now, for the ISD, this is what we will have after DAISY. This is what we can expect with MSC. So again, you can see that we have a real improvement in this region. And here the improvement is even better because with DAISY, we can use only the quasar as a tracer to measure the ISD. And here we can start at 1.6. And what is interesting in terms of science is that as we are at a very high redshift, around 4, for instance, the value of F is very close to 1. So what we are going to measure is not F sigma 8, but it's directly sigma 8. So we are directly going to measure AS. This is the forecast for FNL. So this is just an example of what we can have for the power spectrum with the Lyman Break galaxy. And here, if you assume that FNL is equal to 5, you can see by eyes that we are able to measure it. And now you can quantify this for different category of tracers. So in blue is what you expect with DAISY, with all the tracers in DAISY. Then this is what you can expect with MSC. So when you increase, this is the inverse of the error. So when you increase it, there is really a gain in this direction. So basically with only the quasar, you are the same level as DAISY with all the tracers. Here, this is with the edges, and finally with the Lyman Break galaxy. So this means that the sensitivity that we have on FNL is at the order of 1.8. This is for volume from 1.6 to 4 in redshift. And you can easily imagine that we can go further, for instance, between 2.4 and 5 with Lyman Break galaxy. And in this case, you have a measurement of FNL which is lower than 1, which is a usual goal. This is for the neutrino masses. So in blue, this is what you expect with DAISY. With MSC, you have more or less the same, but as you are going to probe different regions in redshift, you can combine both. And this is what you obtain when you combine MSC and DAISY plus Planck. So this means that you are able to measure the mass difference at the level of 3 sigma. And now if you use CMB S4 instead of Planck, you are at the level of 5 sigma. Just to give you an idea, with this project, you can do better than what you will do with Dune, which is a neutrino beam, and the cost of Dune is certainly $2 million. Billions, I say, okay, 2 billions. It's between 1 and 2 billions of dollars. So, very briefly about the participant in MSC, you have Australia, you have Canada, Chinese people, France, Hawaii, India. You have a new participant, which is University of Texas, and you have 2 observers, NOAO and UK participant. For the cosmology program, we are working on the improvement both the simplification and the optimization of the low and moderate resolution spectrograph. Basically, you have one spectrograph, but you can change the grains to improve the resolution. But in this case, you can cover only half of the wavelengths. So the idea is really to go to a single spectrograph. So here, this is the current design of the spectrograph with 3 arms and 3 visible arms and 1 near-infrared arm. And this spectrograph is very close to the DAISY spectrograph in the design because it's the same people as proposed the design. I mean, this is really in the French community and in Winlight companies that we are working on this design. And so the idea is really to switch to 4 spectrograph, 4 visible spectrograph with 4 arms and with wider detectors. And so this means that we will be able to cover this range in wavelengths with a better resolution at the order of 5,000, and 2 specific spectrographs just for the near infrared. And in this case, we will have both G, J, and H band. So this means that we will have a gain resolution, which is better for the determination of the redshift, which is better also for the Lyman forest. And with the H band, we will have the ability to observe the edges in a redshift range between 2.9 and 3.7. This is the timeline. So we are here in the preliminary design. There is one important date, which is in the middle of 2021, where we have we have this question of Liz about Mauna Kea, but it's not just for MSC or CFHT, it's for all the telescope of Mauna Kea. And after, you can see the timeline. Maybe it's very optimistic, but anyways, at the end, the first light is in 2029. Okay, just a summary. So we have a generic program with 3 tracers, EIGs, Lyman Boy galaxies, and quasars. The redshift range is 1.64, with a possible extension to 5. We have to study this. The surface is 10,000 square degree, and it's a small program, only 100 nights per year for a 5-year program. Thank you.
Questions for Christophe?
Maybe this is not science, but is there any communication between the French community and the European Southern Observatory about the fact that they have kind of 2 similar like projects that are being discussed, but they don't, you know, like between this and Spectel?
Yes. Okay. I think that the idea is what is written here is really to have a generic program. So when you try to find this generic program for the cosmology, you are preparing for these two options. And as you mentioned, you can have an option with MSC and another option is with ESO. And you can imagine that, for instance, if you have a problem with the lease on Mauna Kea or other problem with funding, you can move to the ESO option. That's, I think.
Is there any active discussion in that regard, in that direction?
Basically, all the groups are in the 2 projects, I mean, more or less. So it's the 2 options are really in parallel now. Except that for MSC, you have a design, which is not optimal for cosmology, but you have really a design and with this design, you can do a very interesting program in terms of cosmology. This means you cover FNL, you cover the neutrino mass, and you cover a fraction of BAO and ISD. And it's not a very expensive program in terms of night. It's really optimized for the cosmology. It's just 500 nights, which is not a lot finally. I mean, the strategy is really different to the strategies that you have with MegaMapper or for BOSS, eBOSS, and DAISY. Here, you just want to have a small program for cosmology, but you want to study all the interesting part for cosmology. And the interesting part is really the primordial universe, the measurement of FNL and the measurement of the neutrinos. And at the same time, you can measure the BAO and the ISD. I think it's really a different strategy.
This is relevant probably for the discussion of the panel later. It looks like you are still planning basically to get freshets. That means your spectrum will be just at the synapse noise necessary to see the oxygen 2 doublet and generation, or you are planning to have more signal to noise to allow other science better
Actually,
characterization?
actually, you have several programs in parallel, and for the redshift, I mean, for the Lyman break galaxy, we have optimized to get the redshift, but at the same time, you are going to run the Lyman alpha forest, the quasars. In this case, the signal to noise is at the order of 2 or 3. So it's not just one for the continuum. That's clear that we have optimized the exposure time to get a very safe redshift for the edges. We have 90%. And after, we have something at the order of 50% for the Lyman break galaxy. But actually can be better if you consider the work done by Mike, for instance. I think that we have been a little bit pessimistic in this computation.
Well, let's thank Christoph again. Next we have Dong-hee talking about HETDEX. There's a laser pointer.
I prefer this. Thank you, organizers, for the invitation. I was wondering, first of all, why am I talking the last in this conference and in the section of future survey? But I realized that HETDEX is indeed, HETDEX belongs to this group because the telescope that we're using is 10-meter class, and the number of spectrograph we are using is 35,000. That clearly belongs to the future survey class. So, but it's ongoing. So let's talk about the future class survey, which is ongoing, that's HETDEX. So this is our telescope, 10-meter Harvey Emery telescope in West Texas. You can see the 2.7 meter. And as you can see here, HETDEX is the multi-institutional international collaboration centered around University of Texas. And we got some funding from NSF and Penn State. If you cross the Atlantic Ocean, you have Oxford, AIP, Göttingen, Munich collaborators, and you have University of Tokyo. So this is a summary of what HETDEX will do. HETDEX is the galaxy survey that we are using 10-meter HET. We'll observe 1.2 million Lyman alpha emitters between redshift 1.9 and 3.5. That is 434 degree. So this is a summary of HETDEX. What HETDEX is different from other surveys. This is the first blind spectroscopic survey. Blind means that we don't pre-select our target, just put the fibers and then get whatever signal that we get. And then this is the first 10 gigaparsec cubic scale survey at high redshift, 1.9 to 3.5, with a sufficient number density. That what I mean is that m bar times p, that's a signal to noise per Fourier mode. That's 1 or above 1 per k less than 0.25 h inverse megaparsec. That's roughly the scale that we believe probability theory models the nonlinearities at this high redshift universe. Okay. So we can do this blind survey because we have ridiculously large number of spectrograph. We have 34944 spectrograph. And that means that every 6 minutes we get 34944 spectra. Okay, so that is enabled because we use some instrument called virus. That is the, what's that? Oh yeah. Where is it? Oh yeah, visible integral field replicable unit spectrograph. Sorry, we plan to have 78 units. Right now we have 62 units operating, and each unit contains 448 fibers. Okay, and then for each 6 minutes we'll see whatever light photons out there above between 1 to 5 times 10 to negative 17 or per centimeters square per second, whatever, if that means something to you. Okay. So this is a telescope, and that is the structure. We have primary meter, like about 10 meter. The secondary here, we have the focal plane here, and then that is connected by optical fiber that is connecting the focal plane to the detectors here, and cooling systems are here. And that is the real image of the prime focus instrument, and that is the BIOS enclosure, the where we have our cameras. And this is the image of real cameras that we have. And what we do here is we open the container and put this camera into the container, the cryogenic system. He is our PI, Gary Hill, who designed the instrument. And that is the image at the focal plane. I think we have a little bit more than 62, but not all of these them are connected to the camera. That's why we have 62 working unit right now. So in this two-dimensional unit, that is one IFU, we have 448 optical fibers aligned in two-dimensional way. Okay? And each of them, the one end is square, the other end is like this one dimension. Okay? And if we coated that with a coating, and that's one unit of IFU connecting cable. The one end is like this, that's 448 optical fiber, another end is that. And what you do is the photon come into the telescope and hit here and out there, and we put the slit here and then disperse the light. Okay, that's why we get the spectra of each of these fiber at once. So that is one of the imaging that we combine different frequencies and get this image that's working 62 units. By the end of 21 trimester, we expect to fill all of this 478 IFU plane, then we'll start with a full mode from 22. That's the status. And that's the footprint. We have two fields, Springfield. Springfield is here. And that is, I think, BOSS and EBOSS and JZ footprint. We have overlap. And that's our fall field. Combining Springfield and fall field, we will survey with 9 gigaparsec cubic volume. Even though that looks small, that looks like pretty small footprint, we are at high redshift, means that the radius is large, therefore our volume cover is fairly large. So each of these footprints, we fill that by telescope field of view. So each of circle here are 22 arc-minute field of view. And each field of view is filled with 78 IFU unit. And each of that square, we put the fibers. So that's the 448 fibers. That's how we do the survey. Okay, so every 60 minutes we get spectrum of all of these circles, and then we move the instrument a little bit and get the spectrum of a little bit upside. So we do the 3 dithering to fill this square. So basically that square is filled. Okay, and that's the example data frame. So here y-axis is fiber. So each of them 1 to 148 is connected, named here, and 1 to 448. And then that's the wavelength direction. Okay. And typical line alpha looks like this. We have very small continuum line. That's it. Okay.
This is after sky subtraction.
Yeah, that's right. Yeah, I mean that raw frame is much more noisier. Yeah. And yeah, right. And in terms of density of spectra, Heptax is very nice. So this is the figure from, I have a page here. Kind of rough, I think a while ago. And then we have number of sky area and density of spectrum. You can find your favorite survey. For example, gamma is here. Sloan main Gallup sample, 6DF, and CFA is here. And in terms of this domain, Heptax is here. If you have all spectra, you see it over there. If you count only spectra that we expect to have some object, we are still there. Okay. Because we have so many spectra that do not observe any of the interesting astronomical object, we can use it for sky subtraction. So we have very nice sky calibration done by those redundant spectra. So what do we detect? As I said, we will detect 1.2 million Lebanon traveling galaxies between redshift 1.9 to 3.5. So that means that we'll have about 200 LAs in 20 minutes. On top of that, we'll have about equal number of low redshift oxygen 2, 3727 emitting galaxies, and 0.4 million other galaxies, and then Milky Way stars and AGN. Okay, so that's what we observe. So because of this blind survey strategy, though, we have a couple of challenges that we have to solve. So let me explain that. First challenge comes with this guy, low redshift oxygen 2, 3727 emitting galaxies. This line, as you all know, is the doublet, but our spectral resolution is poorer than the separation, so we cannot reserve the doublet. That is the beginning of the problem. As I show you, Lyman alpha galaxy at redshift 2.25 spectrum. Nothing, nothing, nothing. We have one line. Okay. Oxygen 3 at redshift 0.06 is fairly isolated and doesn't have much feature except for H beta and oxygen 3 5207. But that is fortunate for redshift 0.06. But for the higher redshift Lyman alpha emitters, these two lines go outside of the band. Then oxygen 3 is really look a lot like Lyman alpha emitter with a lower amplitude of line. So that caused a line confusion for us. So our first astronomically motivated way of distinguish them is using something called equivalent width. That is a ratio between continuum to the line intensity. The Lyman alpha emitters are UV in rest frame, therefore the continuum is much lower. Okay. On the other hand, oxygen emitters, as a normal galaxy, is high continuum. Okay. The Lyman alpha emitter has large continuum and large equivalent width, and oxygen emitters have low equivalent width. That's our first order discrimination scheme. So typical Lyman alpha emitter that we have, in our list of sample looks like this. We have a line here. And then, to do that though, we have to measure continuum. Therefore, we have a deeper imaging survey. So now we apply the time for HSC Subaru imaging. So we do have imaging data down to magnitude of 25 in G-band. So if you do see some line on the same continuum, that's very good Lyman alpha candidate, such as this. I think those are the example of how we can see those. But this scheme of using the equivalent width cut is not perfect. So that is a simulated Lyman alpha and oxygen 2 data points in this line intensity and equivalent width plane. The equivalent width of 20 cut is here, but then that cut is not like clean cut, so we have some overlapping. Okay? And in this paper, in the collaboration, Lung et al., they found out that if you want to reduce the interrupter fraction of oxygen galaxies down to 0.5%, you have to pay the expense, which is you lose 6% of LAs. That means you lose something like 6,000 LAs that we don't want to do it. But then what will happen if you just ignore this interloper? Then we have something called interloper bias. Okay, what does that mean? So if you have all those LAs and a few fraction of oxygens, so we define this parameter F, that is the total number of LA to the oxygen interloper fraction. If you have 5% interloper, and that is the constraint that we derive by using the Lyman alpha emitter plus 5% interloper oxygen emitter in DNA length. As you can see here, this is unbiased result, and the bias with this contamination bias the measurement of distance. Okay, that's a serious problem. Why does it happen? Because even though oxygen fraction is small, this can cause a big problem because of this. So let's consider two oxygen 2 emitters. We mistakenly chart this to the higher ratio, right? Okay, and then there are two numbers that are important. Here, alpha is the ratio between two angular diameter distances. So this for between here and there, about 7. Beta is the ratio between the wavelength ratio times Hubble ratio. That's how is this distance charted to that distance. Okay. So what's the effect on power spectrum? That's what you use to measure the distancing. So this is LA power spectrum, that's O2 power spectrum in the rest frame. Because we chart this low redshift galaxy to high redshift, means that you get the small scale power spectrum and artificially boost that to large scale. That shift this power spectrum here, this oxygen power spectrum to smaller K, okay? And then second thing is that you chart this small separation into large separation, and power spectrum is proportional to volume. So you increase the signal by the ratio of alpha squared times beta, the volume ratio between this and that, okay? So you put it like that. But luckily, if you have small interloper fraction, then this signal is reduced by the fraction square. But because you shift and boost, if you add, at the end of the day, the interloper contribution to the real life alpha contribution, you get something like this. It looks like FNL. But luckily though, this signal depends on the angle. So it doesn't actually fool us as a FNS signal. Okay. And this, because of this alpha and beta, they are highly anisotropic. This transfer direction is factor of 7, line of sight direction is factor of 1. So that generates anisotropic distortion on power spectrum, okay? So that is observed LA power spectrum with 10% contamination. That has this weird signature at the lower K perpendicular value. That is due to the interloper. And if you measure redshift, if you do the redshift space distortion measurement, this will of course bias your measurement of F sigma 8. Okay, that's what happens as a function of contamination fraction. That is B sigma 8 and F sigma 8. The true value is here. If you increase the contamination fraction, you bias this measurement. 5% is here. Okay, that's extremely dangerous. It biases the distance measurement as well as the dynamical measurement. Okay. Luckily, though, we do have a way to test that. And my former student, Henry Grasson Gephardt, he solved the problem. The key idea is that Lyman alpha emitters and oxygen emitters, that they are very, very far away. Okay, they're separated very far away, more than 3 gigaparsec H inverse separation. Therefore, if you take the oxygen emitter sample and Lyman alpha emitter sample and cross-correlate them, intrinsically you get 0. You must get 0, essentially, right? But because of this contamination and non-zero FNG, we do generate some cross-correlation. Okay, that is the cross-correlation between observed LAE and observed O2 sample, and that's entirely due to the interlopers. By using that fact, and this is the high signal to noise, right? I plot the signal to noise at each K mode, 3 sigma, 2 sigma, 1. Then Henry can figure out that we can measure this contamination fraction, and then by doing the joint analysis, we put the Lyman alpha emitter, observed Lyman alpha emitter, observed oxygen emitter, and then we do the big analysis, including everything, including the cross correlation. Then we can actually measure this contamination fraction F and G. The G here is Lyman alpha emitters contaminating oxygen emitters. Okay, so here I put the contour in F and G plane. How accurately can you measure this contamination fraction? And this is the best case, the green circle. That's a complete knowledge of power spectrum is assumed. But if you don't know about amplitude and redshift space distortion, then you of course increase the ellipse. But generally, these are 1% in F, and this is 1% in G. So you can measure F and G within 1% accuracy. We didn't include that because we estimate the weak lensing magnification connection, but that's much smaller than this. That's a good question. And that's the worst case. We now marginalize over the power spectrum, in 2-dimensional power spectrum at each value. Then that's the worst case, but you still get the measurement of sub %. So that's a good thing. And if you use this joint analysis method, then you can estimate the distances, dA and h, with unbiased, statistically robust way, okay? And here and there. I think that's the good news. And then all information here comes from the fact that intrinsic correlation must be 0. We do observe some correlation, okay? Of course, we do have some price to pay, and as a function of fiducial, as a function of contamination fraction, uncertainty, I think this is in R, the 8 dA square over H, increases, but not by too much. So you can live with, I think, uncertainty, I mean, the contamination fraction of a couple of percent, okay? And second challenge, I think it was mentioned by Uros yesterday and Sukdeep this morning, is about the line of sight directional effect, because we are doing the blind emission line survey, and the line of sight direction is somehow important direction for us. And there are two known ways to create line of sight direction depending selection effect. That one is by Fishrata, another is by White and Dijkstra. Okay, and this, I think we already explained this. I'll skip that, but this one is using the fact that we detect a line, and you have to include a line radiative transfer effect. And one of the important factor there is optical depth. Okay, and optical depth is related to this quantity. There's a line of sight directional change of line of sight directional velocity. Yeah, that is the factor that we normally include as a Kaiser effect in linear order, and we have additional dependence on that effect beyond the Kaiser effect, just normal F times mu square. Okay, so we have to include that effect, and that is linear order. And the higher order, we have to include more parameters. With my usual collaborators for this matter, Beng Sang and Fabian, we wrote down this paper, completing the perturbative bias expansion, including the selection effect, and then we end up having 22 parameters, 22 bias parameters, including the stochastic bias and all those parameters with selection effect. If not, we have 11 parameters without selection effect. And people teased me for this, including this many parameters. I had to explain we can do still cosmology with that. So in this new paper that in preparation with my former postdoc, Nishan Agawar, we check if we can still do the cosmology after marginalizing over these 22 bias parameters, including selection effect. So that is the constraint on distance measurement and F and primordial shape measurement without after marginalizing 11 parameters and 12 two parameters, okay? If you only use power spectrum, for example, you cannot measure F anymore. It's an uncertainty for fiducial value of 1, uncertainty of 14, right? Forget about it. But if you use power spectrum and bispectrum, and bispectrum can measure most of the nuisance bias parameters, and then our constraint comes back to something comparable to what you expect without the selection bias effect. Okay. So that's another importance of including bias, I mean bispectrum. But can we ignore this effect? Answer is no. So this is the effect of ignoring this selection bias, linear order selection bias. If the true value of selection bias is only 99% of the B1 value that we put in, like means that the systematic effect on that parameter is 1%. And if you ignore that and just fit everything with 11 parameters, okay, this is what happened. So, oh, I see, it's not. Okay. And then I calculate the shift of this parameter in the unit of sigma, okay? And then I misunderstood numbers. It's not 290, it must be 1.4 sigma, same as this. But I mean, luckily, one good thing is that 1% change in this parameter does not bias our distance measurement. That's a good thing. But F parameter, the growth of structure parameter, we cannot measure it. And that systematic bias is order comparable to the sigma. So you have to include that, the selection bias effect, okay? That's our second challenge. Have to marginalize about 22 parameters, okay? So other goals of HETX is we can measure the curvature of the universe to 0.1% level and non-gaussianity of delta FNR of 2, including power spectrum and bispectrum. Also, you can measure neutrino masses, okay? We have studies going on about galaxy evolution and Lyman alpha property and the large scale structure, IGM traced by Lyman alpha emissions. And being the blind spectroscopy survey, we expect to have some unexpected object. And funny story is that we found many meteors. At first, we were very confused. What is this guy? And turns out that it had some track. It was a meteor. We have spectra of a couple of tens of meteor right now in our sample. Okay, this is survey status. As of now, I think we are about 20% complete. This is our Springfield and Fall field, and those small squares in this strip are the reason that we got data at the moment. And we are making great progress. And that's the conclusion. Survey will end around 2022, 2023, and then we'll measure dark energy as well as all these exciting cosmological terms. Thank you.
Questions for Don?
Just really quickly, why do you dither to recover your fill factor? I mean, you're not recovering at interesting modes. Why are you doing the dither between?
That's right.
exposures?
Yeah, somehow we decided to do it from the beginning. I don't remember the exact reason, but yeah, you're right. So this square is about 1 megaparsec, so the dithering is
Yeah.
very small. Yeah.
I mean, I was wondering.
Yeah. That's about megaparsec.
Yeah, that's exactly right. I mean, I was wondering if it was just recovery.
Well, maybe I
As
think
a
that's
combination
for
of
the
functions.
other galaxy science, right? If you, let's say you have galaxy here, and you may want to have like
Okay.
complete covering factor. I think it's
Sure,
not
sure.
cosmology driven decision. I think, yeah.
So to be clear, you are already 20% of the way for the cosmology.
Mhm.
So-
Right.
Because at some point you mentioned that it's not officially starting until you get to the full.
Oh, there was a discussion about that, but then I think we decided to declare the first light. Like, I don't know when was it? October 2017. We just had to declare it because HTT board was very kind to us. They granted all dark time whenever our field is up. So we have to tell the community that we start the survey. Otherwise, it doesn't make sense. Right?
But are you going back to like basically the fields that were observed in the beginning? Are very
That's right.
patchy.
Yes.
So is there a plan to go back to fill them back in, or?
We do have a plan. Yeah. And that should also come with the quality controls. We do have our way to control the quality of data, and then yeah, we do have plan to go back and.
Not sure why.
Yeah. Maybe that PDF is too big.
It's crashing.